So, during the 6th week, I will be discussing an important topic called process capability analysis. In fact, on any say exercise we carry out on quality, or say quality engineering or quality control, the directly or indirectly all sorts of analysis, quality related analysis are related to process capability. So, process capability is considered a very important topic. Now, there will be 5 lecture sessions. In the very first lecture, I will be referring to the basics of process capability and process capability analysis, where I will be referring to the definitions of process capability, specification limits, control limits, natural tolerance limits, and statistical tolerance limits. Okay, so, on the next lecture, lecture 2, will be referring to the process capability ratios and their measurement, and under process capability ratio there are many ratios which are relevant. Some of these ratios as a CP, CPU, CPL, CPK, CPM. Relationship between CPK and CP will discuss, and the selection of the appropriate ratios. What is the basis of selecting an appropriate ratio? During lecture 3, the process capability analysis procedure in detail we will discuss, and particularly the approaches for determining process capability using individual observations as well as using control chart information. During lecture 4, we will be discussing setting tolerances and specifications for component and assemblies. Tolerances on assemblies, that is the first topic. The second topic will be the tolerances on individual components, and the last one will be the tolerances on mating parts. During lecture 5, we talk about measurement systems capability and analysis, concepts of measurement error, gauge variability and total variability, the so-called P by T ratio, measurement of repeatability and reproducibility, components of the measurement error, and estimation of measurement systems capability. So, this will be your coverage under process capability analysis. Now, we will be discussing the few important say the issues related to process capability. We call it the basics of process capability and process capability analysis. So, under definitions of process capability, specification limits, control limits, natural tolerance limits, statistical tolerance limits. So, as a student, as a learner, as a practitioner, you must have very clear understanding of all these concepts. Okay. So, we will be discussing all these the topics. Now, before say discussing this process capability analysis, just I will be taking few minutes of time to discuss the Q-sum control chart. So, I will be just taking, because we have referred to say the 2 approaches for Q-sum control chart. The first one already we have discussed at length, that is the algorithmic say the Q-sum or say tabular Q-sum. Whereas the alternative to algorithmic Q-sum, always we prefer to use algorithmic Q-sum, but because of some reason, suppose you seek an alternative. So, obviously the alternative could be the V-mask template. So, I will be just referring to some interesting features related to V-mask template. So, as an alternative to tabular Q-sum scheme, you may use the V-mask template. So, in this approach, a template called V-mask is used to verify if a process has gone out of control or not. Okay. So, there are 2 parameters in a V-mask. One is the least distance D, and the second one is the angle of each decision line with the horizontal. Okay. So, there will be 2 decision lines you will find in the template upper decision line and the lower decision line. So this is a typical VMask template. You will find that this is the lead distance, and this is your upper decision line, and this is your lower decision line, and you have this angle theta with the horizontal line. Okay, so in x-axis represent the samples, okay, and the y-axis represents the CI. Is it okay? The CI means the cumulative, the deviation from say at a sample I, what is the cumulative deviation of the observations from say the target value. So we have already defined CI. So it is basically CI versus sample numbers. So what you need to do, you need to determine the value of theta and the value of the lead distance. Okay. So how to determine the value of d, the lead distance, and the value of the angle of decision line theta with the horizontal line. That means decision line with the horizontal line. So given alpha and beta, what is alpha? That means once you try to design this template, what you need to do, that means you must specify that what is the probability of making type 1 error and what is the probability of making type 2 error. So these two values should be specified, and as we always say that these two values should be as minimum as possible. Is it okay? And delta x bar is basically a shift magnitude that is to be detected for process mean. So what you try to do, that means you define small delta, that is that is delta x bar divided by sigma x bar. Is it okay? That is the standard deviation of the samples, and this is delta x bar is basically the standard deviation of the sample mean x bar. Is it okay? Now we have these two expressions. That means the lead distance is given by 2 upon delta square natural logarithm 1 minus beta by alpha. If beta is small, and usually it is to be it has to be very, very small and negligible, then we can ignore beta over here. So the expression for d is approximately minus 2 upon delta square natural logarithm of alpha, and the angle theta is given by tan inverse delta x bar by 2k, where k is scale factor, and the scale factor, how do you define the scale factor? A ratio of vertical scale unit to horizontal scale unit. Is it okay? Like say when you use this template, that means x-axis versus the y-axis. So that's the ratio is referred to as the scale factor, and where the k may be assumed to be any value between sigma x bar and 2 sigma x bar. So preferred value is twice sigma x bar. So okay. So this is this way we design the VMask template. And how to use this VMask template? Place template on the plot of CI and the sample number. I have already shown. If we want to check at ith sample point if the process is in control or out of control, ith maybe say 5th sample point or 10th sample point. Okay, place the template in such a way that the point coincides with CI value and OP is held parallel to horizontal line. Is it okay? So this way you use the template. And then what is the decision rule? Decision rule is very simple. If the previous sample values from the first sample to the ith sample plot anywhere between upper and lower decision lines, then that's the area. Okay, the process is assumed to be in control. If any of the sample points up to I minus 1th sample plots below the lower decision line, the process is out of control with an upward drift in the process. Okay. Alternatively, if any of the sample points up to the I minus 1th sample plots above the upper decision line, it may happen, the process is out of control with a downward drift in the process with respect to the given process parameter. So this is the rule of using VMask template. there are a set of assumptions under which V-mask approach is applicable, is obvious. You have to validate those assumptions before you use V-mask template as a reliable tool. So, this point is to be remembered that whatever the assumptions you have in the V-mask, later on we will discuss, we will refer to these assumptions. Now, in a given situation for a given process, if those assumptions hold, then only you are supposed to use V-mask template. Okay. So, concluding our discussions on the special purpose control chart, now let me first define the term called process capability. So, what is process capability? In plain and simple terms, it means ability of a process to produce a part or a component or a product as per its specifications. So, I am assuming a manufacturing process, and so essentially it refers to the ability of the process, okay, to produce as per the specifications of a component. Now, before a process is made capable, its potential must be evaluated. Is it okay? First, you must know that whether a right kind of the process has been installed or not. And if you say it's a right kind of the process, that means in this context we say that whether the process has got enough potential to be capable. Okay. So, in this particular context, any exercise on process capability deals with measurement of process potential. That means the first you check whether it has got the adequate potential to be capable or not. So, you need to meet the necessary condition. Once you are you succeed in meeting the necessary condition, then you check whether you are able to meet, or you have become, or your process is really capable or not. That means it deals with the measurement of the process capability, and you are trying to meet the sufficient conditions. Is it okay? I think so whenever we discuss a topic called process capability, inherently you must we assume that, suppose I say the process is capable. Now that means we assume that the process has got inherent say the ability to be to have the potential. Okay. So, this is the first point to be remembered. So, process capability represents the performance of a process. Is it okay? So, many a time you say that the performance is acceptable. Okay. So, essentially we are referring to the process capability. Now, and whenever you say that the performance is acceptable, or the process capability represents the performance of a process, we assume that the process is in a state of statistical control. That means, what is our precondition? That means before you go for measuring process capability, you first verify that whether the state of the process is acceptable to you or not, whether the process in a state of statistical control. So, which kind of tool you need to use? Obviously, you need to use one or more of the control charts, or the relevant control charts you must use. Now, the process capability analysis represents a procedure to estimate the process capability. Now, it may involve a few things like estimating process mean and the process standard deviation. That is the first exercise you have to do. That means, for that you have to collect data, and after analyzing the data, you will come to know that what is the estimate of the process mean, as well as what is the estimate of the process standard deviation. So, that is the first step. In the next step, what you do, you estimate the form of the relative frequency distributions. You already know what is the frequency distribution, like when we discussed the 7 tools of quality management. So, we have referred to this frequency distributions. So, what you try to do, you estimate the form of the relative frequency distributions of the characteristics of interest. That means, for a given quality characteristic. Estimating the proportion of non-conforming product. So that is actually that is the proportion of non-conforming product is ultimately the measure of process performance. Okay. So what is the objective? So objective of process capability analysis is to know the relationship between the process parameters or the process settings and the product characteristics. So this is very, very important. Okay. Though we will be collecting data initially on quality characteristics, and we will analyze the data related to quality characteristics of a component, but ultimately what you need to do, that means in any process capability study, that means first you go for product analysis, and to what extent the process is affecting the the product analysis. So the relationship between the product analysis and the process analysis is a must. And whenever we talk about the process analysis, essentially it is exercise on determination of the appropriate process settings. Okay, so their values. Any problems with the product characteristics can then be related to process parameters, and remedial actions can be identified on a timely basis. Okay. So the product analysis leads to process analysis. So we'll start with the product analysis. Later on, when we talk about when we take up some case studies or we take up some numerical problems, so we'll discuss the relationship between the product analysis and the process analysis. Now, what are the benefits? There are many kinds of benefits you may have through process analysis. It creates uniformity of output. That is the first thing. As I have been telling you, that any exercise on quality is essentially an exercise on consistency or the uniformity of output. The level of quality is maintained or improved. That means it's the ability to meet the specifications. So obviously it is expected that through process capability, the level of quality you can maintain, or even in many cases as a quality improvement exercise, you might say that the level of quality can be improved. It facilitates product and process design. It assists in vendor selection and control. Okay. And it reduces the total cost by lowering the internal and external failure cost. So it is expected that obviously your goal should be the zero defects through process capability analysis. Is it all right? So obviously if you have zero defects, what you can expect that both internal and external failure cost will be at the minimum level. Now this is just an example, like for the specifications of a component quality characteristic is say 20 plus minus 0.1, say millimeter, fine. We may say that the process is capable of producing under a given process settings 99.5% of the component output within the tolerance range. What is the tolerance range? Obviously tolerance range will be 19.9 to 20.1 millimeters. Okay. Any exercise on process capability refers to understanding of certain terms and terminologies. This we always we insist on, that we will be using certain terms and terminologies related to process capability or related to any topic, and you must have a clear idea. You must know what is the exact definition of those terms and terminologies. So these terms and terminologies will be used, and they are to be defined with respect to the process for which the process capability is to be assured. Is it okay? So the context is the process capability. Now the first term we use, that is the specification limits. The next term we use, already we have defined the control limits. The third term we use, that is the natural tolerance limits. And then we also use a term called statistical tolerance limits. Okay, so let me first explain, let me define what is the specification limits. And when you refer to the specification limits, actually is a general term which refers to for the entire product or the entire system. Now when we say the tolerance limit, actually we refer to the physical quality characteristics, the physical dimensions, right? And in many cases, unless otherwise specified, these two terms are used interchangeably particularly when you deal with the physical dimensions of a product or a component. So, how it is defined? Limits that define the conformance boundaries for an individual unit of a manufacturing or service organizations. So, the conformance boundaries, like in a given case, you may have for a given quality characteristic, say X, so you may have USL, you may have LSL. Is it okay? And here we say that the specification limits can be of two types, like say the single specification limit case, either upper or lower, or it could be the double specification limit case, depending on the quality characteristics you use. Is it okay? So, we have already defined them, in fact, the specification limits. So, now what we try to do, that means we try to define the natural tolerance limits. So, what is natural tolerance limit? That means here you say there will be upper natural tolerance limits, there will be lower natural tolerance limits, where you just refer to the distribution of X, and under certain conditions, in most cases you will find for the running production system, and when the value of X is dependent on the so many other the factors or the variables. Okay, so and X you get from say the downstream, whereas these factors are affecting at the upstream processes. So many a time the assumptions regarding normality with respect to X, this assumption is valid. Now, so you have the upper natural tolerance limit, and you have also lower natural tolerance limit. So, how do you define upper natural tolerance limit? So, mu is basically the process mean. It's so mu plus 3 times sigma, 3 times sigma. Is it okay? And what is the lower natural tolerance limit? That is mu minus 3 sigma, minus 3 into sigma. What is sigma? Sigma is actually the process standard deviation. Now, instead of writing U and TL, also you can write UPCL, that means upper process capability limit, and similarly L and TL is also known as LPCL, that means lower process capability limit. Is it okay? So, so we have defined what is a natural tolerance limit. Okay. Now, what is statistical tolerance limits? Now, the statistical tolerance limit is basically the generalization. These are the limits of an interval, for which it can be stated with a given level of confidence. Confidence level is say gamma, that the interval contains at least a specified proportion 1 minus alpha of the population. Is it okay? So, this is the most generalized definition, and so with an example, with a probability of 0.98, we conclude that 95% of the parts have a part length between 20 and 35 mm. Is it okay? That means I am getting a population. So, obviously, I will get a representative sample, and the sample size is 10, and what I conclude that 95% of the parts from this sample, I conclude that their values will be lying between 30 and 35 mm, and I will say with the confidence, say 95% of the parts, that is the proportion, that is 1 minus alpha. That means alpha is essentially 5%. So, 95% proportions of the parts, and with a probability of 0.98, that means my confidence is 0.98. Is it okay? So, 98% of the time I am sure, or 95% of the time I am sure. In some cases, suppose you are not that sure, you say the 85% of the time I am sure that the values will be lying between 30 to 35. Is it okay? But you also specify the sample size. Getting my point? Now, so this is the statistical tolerance limits, and many a time we refer to the statistical tolerance limits also. Now, What is the centering of the process? This is an important term. Okay, whenever you get a process and you try to improve the process performance, so you carry out the process capability study. So the first thing you must know that how to achieve a condition which is referred to as the centering of the process. When the process mean coincides with the nominal value or the target value of a quality characteristic. So this is very, very important. That means if it is a double specification limit case, you know that usually the desired value or the nominal value of the quality characteristics lies at the midway between upper specification limit or upper tolerance limit and the lower specification limit or the lower tolerance limit. Is it okay? So that is the midpoint. Now if the process condition is such that you are getting the value of the process mean, okay, exactly at the nominal value or the target value, then you say that the process has been centered. So that is the first condition you have to achieve. That is point number 1 for the any exercise on process capability. Now the next important aspect you must be aware of, that is the relationship between the process spread and the specification spread. Is it okay? So as I have already mentioned that what is a process spread? Now the process spread is actually related to this. That means the distance between say upper natural tolerance limit and the lower natural tolerance limit. So that is basically a process spread. So if you assume that UNTL lies at 3 sigma on one side and LNTL is lying at 3 sigma away from the mu, okay, on the other side, then obviously in this particular case the process spread is 6 into sigma. Now what you try to do, that means you first you check that with the data with your observations, you first measure the process spread and then you relate it to the specification spread. Okay, so the relationship between the process spread and the specification spread. So what is the specification spread? So specification spread is basically the distance or the difference between say USL and LSL. So USL minus LSL. Now there may be 3 kinds of relationship between them. So the first one is, see, the process spread is less than the specification spread. So this is case 1. That means most desirable. Why I am saying it is most desirable? Because if you achieve this condition, the proportion non-conforming from the process will be negligible. It will be very, very less. Is it okay? Now always we say that there could be drifting in the process. It may so happen that if you are unable to control the value of sigma, it may so happen that the process spread may increase. Is it okay? Usually the specification spread remains constant, whereas the process spread becomes a function of time. Is it okay? So now suppose the process spread increases and at certain point in time, the process spread is equal to the specification spread. Is it okay? So it is a theoretical possibility. That means momentarily it might happen, but it is also desirable. But still what you find that if you if you use say plus minus 3 sigma limits from 3 sigma from the mu as the upper natural tolerance limit as well as the lower natural tolerance limit, and if x is assumed to be normal, out of say 10,000 pieces you produce, is it okay? So 26 parts you may find as non-conforming. Is it okay? So that is cannot be avoided, but this is just in a transitory phase, and you will have these conditions. But then again, if you the third condition you will arrive, that means where you lose control on the sigma. That means the process spread is increasing, and ultimately you reach to this undesirable state or undesirable condition, that is the process spread is becoming greater than the specification spread. That is case 3, it is most undesirable. Now before I conclude this session, So I will just refer to one aspect, like that is how to address the problem of case 3. Case 1 is acceptable. Case 2 is also acceptable, but you are on toes. You must be able to, that means slowly, very soon, you may lose control on the value of sigma. So that is to be avoided. So usually, you from case 1, you may directly go to case 3 in majority of the cases. So how to address the problem of case 3? Now there are 4 alternatives in order of preference. So first, the alternative could be by increasing the specification spread. That means whose responsibility is this one? Basically the designer responsibility. Many a time what we have found that unnecessarily you may have a very tight tolerances. So whether the design department can, or the designer can change the specification spread. That means instead of very close tolerances or the tight tolerance, can it be made slightly loose, okay, wide, okay. So if that is feasible, no problem. That means the process is a high chance that the process will be producing very less number of non-conforming units. If this is not possible, then you go to the next one by decreasing the process spread. How do you do this? As you know, there is a point to be noted that the sigma of a process is basically represents the inherent characteristics, and it depends on what sort of the design you have. So if you change the process altogether, which is the better technology, now the decreasing the process spread is possible. If this is not feasible, suppose for that you need investment, it's a new technology, the new process, okay, you have to install. Suppose this is not possible, then what you do, the third alternative, by achieving a desirable balance in the proportion of the scrap and rework. Is it okay? This you also do. When you take up an example, you will find that always you try to avoid the scrap, because between scrap and rework, if you compare, obviously the scrap will be more expensive. So you change the settings in such a way that the proportion of rework will be more, say 90% of the cases, whereas only in 10% cases in the scrap. If you do that, okay, obviously there could be improvement in your performance. And if suppose all these 3 alternatives are not feasible, you tried your best but you have failed, then what to do? You have to go for 100% inspection to eliminate non-conforming units. That means as and when they occur, you must be prompt enough to remove them from the system. So with this I conclude this session.